Welcome, everyone. We're going to let everyone file in and we'll get started momentarily. All right, well, let's go ahead and get started. Thank you for joining us, spending your morning or afternoon with us from wherever you're joining. My name is Dan Jeline. I'm at the UNC Highway Safety Research Center. Together with VHB and the Federal Highway Administration Office of Safety, we're delighted to bring you this webinar, which will focus on improving pedestrian safety through vehicle design and technology, being delivered through the Pedestrian and Bicyclist Focused Approach to Safety program. So we've got a great panel. I'll introduce them to you shortly and talk a little bit more about the webinar. We are presenting a disclaimer here that we're contractors presenting this information in our own research. It doesn't reflect the views of US DOT, and we're not endorsing any products, manufacturers, things like that. For logistics, you can post questions, send them to us through Zoom at any time. We're saving some time at the end for discussion. So just because we don't answer it right away doesn't mean we don't see it. We'll pull together that list of questions for the discussion period and do that all together at the end. If there's anything urgent, technology related, anything like that, put a question there and I can try to respond to that very quickly. The webinar slides and the recording will be posted at the link here. I'll send that out to you momentarily. The slides are there already. The recording will probably be up sometime tomorrow or early next week. Continuing education credits will be provided. We're going to get you a link to a post-webinar questionnaire. If you complete that, you'll be able to receive your certificate of attendance for the webinar. So that information will all be coming to you, again, with a link to the archive page in an email later today. We've got a few objectives with the webinar today. Obviously, we want to learn about what role vehicle technology and vehicle design play in determining both the likelihood and the severity of crashes involving pedestrians. And we want to be able to help you identify vehicle design and technology improvements that can improve safety for people outside of vehicles. And we finally want to just bring some of the lessons and key takeaways back to your localities, your regions, your states, and help inform your pedestrian safety initiatives. I'd like to introduce the panelists who are joining us today. You'll first be hearing from Dr. Samuel Monfort, who's a statistician, at the Insurance Institute for Highway Safety. Dr. Monfort joined the Institute in 2018 and studies topics related to predicting crash risk. His research is focused on the impact of recreational marijuana legalization, factors that affect pedestrian safety, and how vehicle size and weight can affect crash outcomes. Sam is joined by Becky Mueller, who is a senior research engineer at the Insurance Institute for Highway Safety. Ms. Mueller develops new crash tests for IHS vehicle ratings that reflect unaddressed real-world scenarios in which injuries occur. Her work led to an updated side test and the first passenger side frontal test in the Institute's suite of evaluations. Ms. Mueller has also researched injuries of vulnerable road users, advanced crash test dummies, and new injury metrics. Greg Bannon is also joining us today. Greg is the Director of Automotive Engineering for AAA. In this role, he oversees all automotive research and testing for the 65 million member organization. Areas of expertise include electric vehicles, advanced driver assistance systems, autonomous vehicles, automotive batteries, and fuels. Finally, we're joined by Dr. Alexander Epstein, who joined the US DOT Volpe National Transportation Systems Center in 2011, where he leads surface transportation systems safety initiatives spanning local, state, and federal transportation agencies. Dr. Epstein oversees research, analysis, and demonstration partnerships with fleets, industry, and nonprofits to assess the safety and sustainability benefits of improved vehicle designs and technologies. As I mentioned, we're going to go ahead and get into the presentations, and I'll ask Dr. Monfort to go ahead and pull up his slides when he has a moment. I want to remind you all that we are going to be holding all the questions for the end, but submit them anytime, submit them as soon as you have them, and we'll go ahead and start queuing those up. So Sam, I see your slide. Please go ahead whenever you're ready.
All right, Dan, thanks for the introduction. Thanks to all of you for being here. Like you said, my name is Sam Montfort. I'm a statistician here with the Insurance Institute for Highway Safety, and I'm going to be sharing with you some of the results of our pedestrian research initiatives. So the reason that we're so interested in pedestrian fatalities is precisely because they've been increasing so much over the past few decades. In fact, we got down to a low in 2009, and since then, they've increased 83%. Uh, Obviously, a huge increase, nearing record levels. And so we at the Institute have been looking into the factors that might be predicting those fatality outcomes. Now, one thing that comes to mind and came to mind for us as well is the changing makeup of the fleet. So today, as of July 2023, 55% of vehicles on the road are SUVs, and this is a figure that has increased quite a bit since around 2009, and really, or from earlier as well. But what we're seeing now is a rise of these larger vehicles, and some past work has found that these vehicles increase risk to pedestrians that they hit. So that was definitely one avenue that we want to take when understanding this problem. But another one is that not only are SUVs becoming more prominent, pretty much all vehicles are getting heavier, bigger, and more powerful. So these are three charts representing the average curb weight in pounds of vehicles in the US fleet, average length in inches of those vehicles, and the average horsepower that they have. And as you can see, it's increases across the board. And this is especially true among pickups, which another factor that's been featured in a lot of media recently are the very large flat fronts of certain pickup models, and that's definitely something that we've observed quantitatively as well. So, like I mentioned, there's been a lot of good work studying this, and generally speaking, what they found, kind of just to set up what I'm going to share with you now, is that taller vehicles inflict more damage to the people they strike. I mean, this is not terribly surprising, but what they find is that the hip height of the pedestrian relative to the vehicle front end is a key predictor of certain crash kinematics. So a crash kinematic is essentially what happens to the person after they're struck. Where do they go? And it also predicts injury outcomes. Um, we find um, that these taller vehicles in general tend to imperil people. But unfortunately, a lot of the research has been done on either older samples of US vehicles or on sets of vehicles from other countries. And so, for example, in Europe, American style pickup trucks are not very common, and vehicles in general tend to be smaller. And so, our approach here was essentially to repeat some of these findings, expand on this research, and really focus on the current fleet composition of the US today. Because again, our main goal here is to understand how the growing US vehicle fleet influences pedestrian injury patterns. So before getting into the findings, I want to describe our data sets to you. We had three excellent sources of data to use here. The two on the top were very in-depth sets of crash data. So we had a set from the International Center for Automotive Medicine, which was a part of the Vulnerable Road User Injury Prevention Alliance. And this group took a set of crashes that occurred in Michigan and delved into the records. So they looked at the medical records, they looked at the police records, they did witness interviews, and they actually went so far as to reconstruct each crash using simulation software to really nail down which part of the vehicle hit which part of the pedestrian and caused what injuries. Um, a more recent set of data from NHTSA produced a very similar sort of crash record, again linking individual injuries to striking components of the vehicles, and again reconstructing the crashes using some simulation software. So, in general, these are two sets of very detailed and very reliable pedestrian crash records. The downside of having very detailed crash data is that you can't collect very much of it. So as you can see up there, that's just about 300 crashes. But oftentimes you want to make conclusions using larger data sets. And so that's where some of these state crash records come in. So I'm going to be sharing with you next the results of a study that we did using this kind of data. So it involved nearly 18,000 pedestrians from police-reported crashes around the United States. These crashes, like I hinted at before, contained less information, so we just focused on fatal or not. So using the state crash data, what we wanted to see was, are certain vehicle front-end shapes linked with more severe crash outcomes? So if we consider a baseline of one of these sort of typical passenger cars, what does it look like when you compare taller and differently shaped vehicles to them? So when I say differently shaped, the facet that we settled on was essentially sloped versus blunt. So you can think about a blunt front end as being pretty much flat from the bumper up to the hood leading edge, whereas a sloped design has a bit more curve to it. And I'll show you a silhouette to demonstrate what I mean shortly. But first, what we found is that tall vehicles overall were much more likely to result in a pedestrian fatality. So what you see here are blue shaded depictions of those tall and blunt and tall and sloped vehicle front ends. And what we found is that heights over 40 inches produced more fatal crash outcomes for pedestrians that were struck. Front end shape did matter though. In fact, what we found is that as you decrease the height a little bit, it was the medium and blunt front ends that elevated crash risk. In other words, if the vehicle is tall, it doesn't matter what shape the front end is. But if the vehicle is intermediate, somewhere between low and high, then that's when that front end can start to make a difference. In fact, when you compare low and sloped against low and blunt and medium and sloped, you get a similar crash risk all the way down. And this is important because every single pickup in our sample had a so-called problematic front end, either tall or medium and blunt. And for that matter, more than half of SUVs did. So this is really kind of like I hinted at before, this seems to be an issue that's mostly evident among SUVs and pickups. You know, experientially, you can probably testify that those tend to be the larger vehicles, but they also tend to be the ones with flatter front ends as well. On the other hand, none of the cars in our sample qualified as tall, and only a subset of them qualified as medium and blunt. So again, SUVs and pickups especially tended to be the vehicles responsible for these undesirable crash outcomes that we saw. So why is that? So we have that more complicated crash data that I mentioned. And so we wanted to get into what was actually happening with these vehicles. And so what we have here are two graphs. On the left, we have the risk of injury, so just the chance of getting an AIS 2+ injury. So that's something more than just a scrape or a scratch. And then on the right, we have the average expected injury severity. So those kind of go hand in hand in many ways. There's the risk of injury and then the average severity. And what we found is that tall vehicles across the board were associated with greater head injury risk. So regardless of vehicle shape, you had more severe, on average, head injuries for these tall vehicle crashes. On the other hand, tall and blunt vehicles specifically tended to injure the torso and hip more often and more severely. So think mid-body mid-body injuries, or these torso and hips, tend to be more severe for these tall and blunt vehicles. But those head injuries tend to be worse across the board for those head injuries, which may help explain why we saw similar fatality risk for tall vehicles across the board. So what happens after a pedestrian is struck? So what we're finding is that pedestrians struck by tall and blunt vehicles tend to be especially likely to be thrown forward after impact. What does that mean? So when you're struck by a vehicle, there's a lot of different outcomes. So you can either be thrown forward, you can roll back and then be thrown forward, you can roll back and then go over the vehicle. So there's many different kinematic outcomes. But what we found is that these tall and blunt vehicles tend to concentrate their crash force all at once, hit you, and throw you forward. This is bad because of that concentration of crash energy. There's less time essentially for the vehicle to impart that kinetic energy onto you, but it's also bad because it puts you onto the road and you're at greater risk to be subsequently run over. And again, that seems to be unique to these tall and blunt vehicles. And it's not just crash injuries and kinematic outcomes that are different. It also seems to be affecting the injury risk associated with crash speed as well. So one of the most powerful predictors of crash injury outcomes is the impact at which you were struck, and what we're finding is consistent with that. But it's more complicated. So the chance that a pedestrian is injured after being struck by a motor vehicle at a certain speed depends on the shape of that vehicle. At very low speeds and at very high speeds, you see similar sort of outcomes between cars and pickup trucks and larger vehicles in general. But at those mid speeds, you see quite a large divergence. So what we found, for example, is that at 30 miles an hour, the median height car has about half the serious injury risk associated with it than that the median height pickup does. And this is concerning again because of the rise of these vehicle types on the road today. Um, I'm going to hand it off now to Becky, who's going to present other work that we've done on vehicle front end height.
All right, thank you. So for this analysis, we once again looked at that in-depth data where we really have detailed information about the crash, the injuries, all of that. But we're going to kind of flip it on its head. So instead of looking at vehicles by category in terms of height, we're actually going to be looking at the pedestrians because pedestrians can, vary greatly in height. So we want to look at the pedestrian hip and waist height relative to the front end height of that vehicle. So we have three categories that we were looking at where the hood leading edge is below the pedestrian. So in other words, the pedestrian's much taller than the vehicle front end. We have crashes where we're looking at the hood leading edge is approximately at the pedestrian's between their hip and waist height. And then vehicles where the hood leading edge is much taller than that pedestrian hip or waist height. And so these would typically be taller vehicles. And we wanted to look at these torso injuries because as Sam's study had shown before, there seems to be a correlation that the taller the vehicle, the more likely pedestrians are to sustain those MAIS2 and MAIS3 plus injuries to that torso region. So we wanted to see what else can we look in more detail at this. Next slide. We looked at the torso overall, and then we also looked at the individual body regions that comprise that torso area. So the thorax, the abdomen, and the spine. We found that between the ones where the person is much taller than the car height, and then the ones where the vehicle height is much taller than the person's hip and torso, we found a significant difference. So as the vehicle gets taller relative to the pedestrian, the outcome, the probability of getting an AIS2 plus injury to any one of those body regions increases. And it's especially true between those very short vehicles and the very tall vehicles. Next slide. The thing that we really wanted to drill down to is where are these injuries coming from? And the big difference between those shorter vehicles and the taller vehicles is really the prevalence of the injuries coming from that front end of the vehicle. So these very tall pickup-like large SUV-like vehicles, we're seeing a large proportion, a little over 30% of the torso injuries are coming from the components like the headlight and the grille and those front fascia components versus we're seeing a lot more of those injuries coming from the hood and the cowl area for the shorter vehicles, either the medium height or the very short vehicles. And what does this mean in terms of how can we influence vehicle design is the real question. Next slide. We'll talk a little bit about that. What we're seeing is there's different kinematics associated with this as well. So when the pedestrian hip is much higher than the hood leading edge, the pedestrian's more likely to roll up the vehicle and also translate up the front of the vehicle, where we might see heads hitting windshields and A-pillars and those kind of things, as well as a somewhat indirect hit to the torso. When we have the hood leading edge is approximately between the hip and the waist height, we see the pedestrian typically getting stuck and rotating around the front end of the vehicle, more likely to maybe hit their head on the hood of the vehicle, but also have their hip be pinned by the vehicle, and have a somewhat indirect hit with the rib cage, the torso region. When vehicles are much taller than the hip and waist height of the pedestrian, it's almost like a brick wall is hitting that pedestrian. And so the head might rotate around and hit either the front end of the vehicle or the very front part of the hood, but it's a very direct impact between those front end components and the chest area and the pelvis. And so these are very different scenarios. How would we, test and evaluate vehicles for these different scenarios? Next slide. We are really trying to look at understanding what kind of tests either we or NHTSA or other organizations can apply to these vehicles to address those very different kinematics we're seeing, very different injury patterns and injury sources, and really focus on, is there something that can be done from an impactor test standpoint? We know that organizations like Euro NCAP have head impacts and leg impacts, but this torso region is something that has not yet been addressed. There are folks working on developing an impactor test for the thorax, but we want to be looking at not just making sure that this impactor test works for vehicles in Europe, but it also could be applicable to all the types of vehicles, especially those American-style pickups that we have here in the US that may be unique, and there may be limited data on understanding that. What we do know is that the tallest of these vehicle categories, these large SUVs and pickups, are associated with the largest proportion of those AIS 2+ torso injuries, and often result from those front components, the headlights, the grille, the front fascia, compared to medium and short vehicles where injuries are coming from the hood and the greenhouse. Our message is that those tallest vehicles should not be ignored or exempted from any kind of pedestrian vehicle assessments, and more research needs to be done to ensure that the testing conditions that someone would propose promote countermeasures that are real-world relevant. So they're reflecting the actual impact sources and conditions that are happening in the real world. So no one-size-fits-all method for assessing these vehicles. These may be very different methods of assessing a small, short vehicle versus a tall and blunt vehicle for these kind of injuries. Next slide. So we've got an ongoing research project going on with the University of Michigan, UMTRI, to look at the effect of these different front end shapes and sizes and stiffnesses on the prevalence of these torso injuries. We're looking primarily at these very tall, boxy front end vehicles, and we want to learn more about how much can vehicle design, mainly changing subtle aspects of the shape and size of those vehicles, influence the prevalence of those torso injuries. Next slide. So we're working with them. They have experience using these kinds of human body models, finite element models. They've worked on developing a series of different front end shapes that represent the wide range of vehicles that exist here in the US. And they're going to be running a parametric study of about 300 different simulations, looking at a range of those impact speeds. In those speeds where, Sam had mentioned there's a big difference between whether the vehicle is short, or the vehicle is tall, and the injury outcomes. We're looking at different sized pedestrians as well, from the 5th female all the way up to the 95th male, in different human body models that are, made specifically for this pedestrian crash environment. And we want to understand where they're impacting on these vehicles, what kinds of injuries could be sustained, and in what scenarios could these injuries be mitigated, and to what extent. Can changing some aspects of these tall, blunt vehicles improve the torso injury outcome a little bit, or can there be big gains? If there are not the big gains to be made by vehicle design traditionally, what out-of-the-box things can we think about to maybe make up those differences? So things like external airbags, or looking at other innovative things that we can do to try to really address those injuries for the very tall vehicles that we know are disproportionately causing a large amount of these injuries. So this is a study that's ongoing. We're hoping to have this wrapped up at the end of the year, and we will likely then do a follow-up study where we look even more detail at what could a thorax impactor test configuration do to help us assess these vehicles. Next slide, please. So that is basically the summary on what we're planning to do here. So we want to understand those torso injury sources for a category of vehicles. We want to understand those torso injury sources across vehicle categories, and what are the potential types of effective tall vehicle countermeasures for the torso. Next. Something else that we're looking at, a different aspect of pedestrian safety, is looking at blind zones. We want to put it from the driver's perspective. How many of these pedestrian crashes are occurring because a pedestrian is caught in a driver's blind zone? And we have developed a method for measuring driver direct vision, that we can compare different vehicle models. And we can also compare, we've got 2 different driver eye perspectives. So a 50th male sitting in a kind of our mid-track average position, and a small female sitting further up in the vehicle. How do different drivers see for a given vehicle? And then also, how does a given driver see across a variety of vehicles? And this is very new research that we're doing. We're also hoping later this year to have a study where we compare some real-world crashes to the blind zones that are in those vehicle models, to see if we can correlate larger blind zones mean greater chance of hitting pedestrians. So stay tuned for those results, as well as some studies where we look at a wide range of vehicles and really compare for the US fleet, from everything from a mini car all the way up to a large pickup. What are the kind of blind zones that are occurring in these vehicles, and what can we maybe do to reduce some of that, either whether it be changing vehicle structures, or promoting vehicle technology that helps alert the driver to the presence of a pedestrian in a blind zone, are things that we hope to analyze on the horizon. And I believe that you will also be hearing more about blind zones and a method very similar to the method that I'm presenting here later on in today's webinar from Dr. Alex Epstein. So with that, I will hand this back over.
Thank you. Becky and Sam, before we move along, there was a clarifying question about the acronym you used throughout the presentation, HLE. Could you redefine what that is or what
That is the hood leading edge.
Okay.
So it's the height of that front portion where it kind of transitions from the hood going up to the hood going back.
Excellent. Thank you so much. I appreciate it. We'll get into more of the questions. We've got some great ones coming in a little bit later, but thank you for that presentation. Very enlightening. We're going to move along now and ask Greg Brandon to continue the discussion. Greg, ready when you are.
All right, thank you.
Sure.
Okay, should be seeing my screen there now. It's in presentation mode.
Yep, we've got it.
Okay, great. Thanks for having me today and talking a little bit about some of the work that that AAA has done and my team has managed regarding pedestrian detection systems. If you're not familiar with AAA, we're the world's largest motor club. We've been advocating for safe automotive systems since 1902. We were formed as an advocacy organization back when we were arguing for equal rights of the newfangled automobile alongside horse and buggy, and we're still doing that today. I run a team of engineers on both coasts that looks at, we really are focused on advanced vehicle technologies, and that's everything from advanced driver assistance systems for this context, all the way to different fuels and electrification, everything in between. But since 2013, we've been analyzing different advanced driver assistance systems, and related to the presentation that Becky and Sam just provided, you know, pedestrian detection systems are something that we really felt it was important to get a look at here. And this study is a few years old now, and we're in the process of refreshing that. But it would be great, regardless of the hood height or the vehicle design, if the vehicle didn't hit the pedestrian to begin with. And that's really the point of a pedestrian detection system, or pedestrian AEB, or automatic emergency braking, for this scenario. And so we wanted to look at not only sort of the basic functioning of these systems, but also some of the more challenging situations that we found where a pedestrian was most likely to be struck or killed. And some of those scenarios outside of broad daylight in an intersection include things like a child pedestrian coming out from between parked cars, a pedestrian right after a curve, as well as two pedestrians just along the roadway walking alongside the road. But most importantly, we also wanted to look at the performance of pedestrian automatic emergency braking at night. The data shows that approximately 75% of pedestrian deaths happen at night, and I think you'll see from the results that that if you were designing a system to do the most good, you might end up in a different place than we're currently at. So first, we'll look at sort of the most basic scenario, and the one that is pretty similar to what the European standards at the time had in place, and now looking at some of the things that the proposed FMVSS 127 standard offers as well. This is the daytime scenario where the pedestrian crosses in front of the vehicle, and the vehicle, if no braking is applied, would strike the pedestrian at the center of the vehicle. We tested at a couple of different speeds because we felt like the lower speeds, while interesting, didn't offer the situations where most pedestrians were injured. So we tested at 20 miles an hour and at 30 miles an hour. And you can see at 20 miles an hour, we had 100% of the vehicles we tested had a notification that there was a pedestrian in the roadway. Unfortunately, they were only avoided a collision with that pedestrian some 40% of the time. And at 30 miles an hour, the effectiveness of the systems really went south, with only one test vehicle avoiding the collision at all, and then in that case, only 2 out of 5 runs. So as you'll see in the video here, I'll go ahead and roll. There's a significant amount of variability in the way these systems work. right, so we'll move on to the next scenario here. That is the one with the child darting out into traffic, and we say darting because it's moving at a little quicker pace than the adult pedestrian in the scenario we just saw. We looked at this at both 20 and 30 miles an hour, and unfortunately, in the case of the child pedestrian, a collision occurred almost 90% of the time. And at 30 miles an hour, none of the test vehicles avoided the collision with the child. As it's noted there, we weren't terribly surprised by these findings, as most of the owner's manuals show these type of limitations. Unfortunately, the owner's manuals don't always track with the advertisement for the vehicle. So let's look at the scenario. So unfortunately, stopping after the pedestrian is struck is, in this case, not terribly helpful. Move on to the next scenario we looked at here. Again, 20 and 30 miles an hour, and this is basically two adults walking down the road. One adult slightly in the path of the vehicle. We tested at both 20 and 30 again, and we found that unfortunately, again, a collision occurred 80% of the time at 20 miles per hour, and at 30, only one vehicle avoided the collision on one run. So again, consistent with the expectations of the system, but this is a very basic scenario where a pedestrian is simply walking down the road. So let's watch the video here. All right, so get into some very interesting findings. I've left out, in the essence of time, I've left out the research that we did around a curve. The short version is they were completely ineffective around a curve. And I think you'll see with the nighttime effectiveness of the system that there is a tremendous amount of work to do. Whenever you consider that 3/4 of the pedestrian deaths happen at night, and the systems all were completely ineffective. So we'll watch some of the videos here on that. So that unfortunately is not a good result. As I mentioned earlier, we're going to be revisiting the nighttime portion of this testing here actually in a couple of weeks, and we're very anxious to see if the vehicles have gotten better over the past few years at detecting pedestrians at night. We're also going to look at the implications of a roadside worker wearing the clothing that they should be wearing along the roadside, and see if the systems work in that scenario. So our recommendations here fairly straightforward in that this is really focused on drivers and regulators. Is that for the drivers, you need to drive these things like they are not there. And if you're in the situation where the pedestrian detection and automatic emergency braking may help, that's great, but you definitely should not rely on it, and encourage yourself to engage in things like looking at your phone, because you 100% we cannot rely on these systems to avoid a collision with a pedestrian. For the auto manufacturers and the regulators, our message was that hey, if you're going to focus on one thing, make these systems work at night when pedestrians are actually dying. And the good news is the regulators heard that. The bad news is the automakers are sort of fighting that new regulation at the current time. And so TBD on what the outcome of all that's going to be, but we're hopeful that the sort of the persistence on the message that if we want to do the most good, these systems definitely need to work at night. And then I understand in this audience there's several highway planners and the like. You can see that that of course the nighttime effectiveness is the biggest limitation. One way to help solve for that is the presence of overhead lighting and the importance of that in places where pedestrians are most active. Unfortunately, most of those nighttime deaths occur outside of intersections, and so we have to think about that and create some interesting ways to get light on these pedestrians. One of the challenges is that the current technology for pedestrian automatic emergency braking relies heavily on cameras, and cameras can't work without contrast. So that's an unfortunate aspect because it takes light to create contrast on the target or the vulnerable road user in this case. And so it's just extremely critical that we consider both the infrastructure as well as the regulation and the design of the vehicles themselves. So with that, I will stop and turn it back to Dan.
Thank you, Greg, very much. Those videos were great, and as well as the content itself. But we got a few requests for, can I get those videos? Can I see those separately? So maybe if you could shoot me a link at some point to those, I'll share that out with the group.
Absolutely, you can find them on our newsroom.aaa.com as well.
Great.
But we'll send a link.
Thank you. All right. Well, we have one more presentation. Dr. Alexander Epstein will share some of the work that Volpe has done on this topic, and then we'll bring it back together for a discussion. Alex, whenever you're ready, you can go ahead and share your slides.
Sounds good. Will do. Let me know if that is tracking.
Great. Looks perfect. We're seeing the program, and then when you go into presentation mode, I'll let you know when we see that as well.
Yes. Let's go ahead and do that.
Great. Perfect.
All right. All set then. So let's see. Thank you very much for the opportunity. I think this is a really good flow of presentations with Sam and Becky talking about the vehicle design, and Greg speaking to the ADAS systems capability and limitations. I'm going to speak a bit more about some aspects of both vehicle design and technology and their implications for infrastructure planning and operations. So taking a bit of a step back in this presentation, and I do want to acknowledge this is the work of many people at the US DOT Volpe Center where I work, as well as many of our colleagues across the department. It's also collaboration with Becky and others at the IIHS and with other organizations such as MassDOT. So just taking a quick step there. Notice this is not official information that I'm giving you on behalf of the US government. These are recommendations that are, or observations that are based on the best technical judgment of Volpe Center staff and not to be misconstrued as policy or guidance of the department. So having said that, and also thank the City of New York, City of Boston, and again, many of the many partners we've worked with on this work. I was pleased to see, thank you, Sam and Becky, for showing this earlier on. This is a slightly different way of stating the same problem, which is if we look at the national data set on fatal crashes since 1975, the beginning of record keeping, we were making a lot of progress on reducing pedestrian and cyclist deaths in this country. And when you normalize it, unfortunately, we've lost about 40 years of progress in the last 10 years. We're back to where we were in 1975 when it comes to pedestrian and cyclist deaths, if not more. Meanwhile, motorist occupant deaths have generally gone down, although still not as much as we would like. With that, we ask ourselves, what can be done? What are the safety issues and countermeasures to reduce some of that trend? One observation is the increasing prevalence of speeding-related deaths. Speeding is now implicated in about 30% of traffic deaths and rising over the last several years, and doesn't seem to be reducing. One area that we identified, and we have longstanding collaborations with some of our overseas counterparts, is what is the full toolkit here? We have an established toolkit for speed management that across transportation engineering encompasses regulatory speed signage or speed feedback signs or automated enforcement, safety cameras, changing the road design with either quick or capital infrastructure investments. And each of those has some limitations. They can be highly effective in some cases, but either the effectiveness is limited in terms of reducing speeds, or they may not be very fast to deploy. For example, reducing speed limits, signs are quick to change, but they're not particularly effective. Now, there's some effectiveness, but to a point. And similar for road design, it can take a long time, decades, for capital projects to get planned and funded and executed. Now, there's one other tool in the toolkit, and this is intelligent speed assistance that really until recently had not been widely considered or even had wide awareness in the United States. Something that also potentially can reduce fuel consumption and improve fuel economy. It could be fast and effective, and that's something that we're seeing now with a wide range of both international and domestic within the U.S. Programs and initiatives and pilots. And so this is something that we identified early on for the City of New York in our Safe Fleet Transition Plan collaboration with them in 2017. Years later, this led to an ambitious pilot that used the availability of aftermarket devices for intelligent speed assistance. Just to be clear, what is intelligent speed assistance? It's a technical solution on board the vehicle to help the driver avoid inadvertent speeding. It can also be for habitual speeders to prevent their intentional speeding. And really, it piggybacks on the telematics and other ADAS systems that we have on vehicles today, which is why it's broadly available. And we actually have a current project right now where we're looking at private as well as public fleet adoption of the technology that tells the driver what speed they're supposed to be going and helps them adhere to that. Now, with this intervention, the question was a few years ago, is it effective? And we were lucky to be able to work with the City of New York on a large-scale evaluation. The City of New York has 30,000 vehicles, give or take. And initially, in 2022, they were able to get 50 vehicles outfitted with aftermarket devices, aftermarket intelligent speed assist. This later increased to 500 as we began to work on this effectiveness study. What this allowed us to do over the period of about 2 years and 2.9 million miles driven was to analyze truly in a 2x2 fashion, control and treatment before and after. What is the impact on driving behavior? And the impact on driving behavior was actually surprised us to some degree with how effective it was. Although because we'd already talked with Transport for London with their fleet, it was almost surprisingly identical to the effect that they observed when they installed aftermarket ISA on their fleet in England. So about 64%, about 2/3 decrease in driving over the enforced speed. And another key point is this worked whether or not the driver tended to speed highly or whether or not, or if they were habitual speeders who had accrued multiple violations over the years. They still decreased the amount of speeding time by about half in that case. And another interesting observation was we were able to bucket this both geographically and in terms of speed limits on the network. Within the City of New York, speed limits ranged from 25 to 50 miles an hour, and the greatest decreases were actually on the faster posted speed limit roads. So that's an active area of research for us at Volpe. Another area of research, this was also alluded to earlier, is blind zones. It's difficult to avoid a crash when you don't see the person around you, and that's the fundamental challenge with vehicle design limitations on driver direct visibility. These are two infographics that Federal Highway Administration created in the last year or two that highlight this issue, let's say in an SUV at left with a school zone or with a large truck and a family crossing in a crosswalk at the right. In real life, how might this work? This actual scenario I encountered near Volpe. A truck driver pulls up to the stop line that's 4 feet in front of the crosswalk, which is the manual and uniform traffic control device's minimum standard. They're doing everything correctly, but the vehicle design obscures their visibility of most of that family crossing in front of the driver. And based on our analysis of available crash databases and some imputation, we believe it's over 700 fatalities a year, based on past data from UMTRI, based on not-in-traffic surveillance and other data. And it's the hoods, the belt lines, the pillars, various geometric elements of the vehicle packaging that make it difficult for the driver to see. And just to put a finer point on that, from the driver's perspective, here's what we're calling the direct vision area in green, the indirect vision areas in blue, and that's mirrors and cameras. In other words, there's no line of sight, and everything else is the blind zone here in pink. And for a large truck, like pictured here, the blind zone can be a significant part of the area around. This is something we've been studying, just as I was saying earlier, going back to at least 2017, and not to belabor this, but this is a highly cross-disciplinary issue that affects pedestrian safety, vehicle design, infrastructure design, operations, and engineering, and so has certainly many stakeholders, and will continue to have many stakeholders in addressing and understanding this challenge. One of those collaborations with those stakeholders allowed us to better understand the linkage. While it may be intuitive that if you can't see someone, you can't avoid crashing into them, the next question is, if you do see them at some point, can most drivers figure out that someone is still there and avoid crashing into them? So in the common scenario where the driver is at a light, so just like I showed you that photo earlier, the truck driver stopped at a stop line and people are crossing in the crosswalk. That driver was in a low vision truck with a large hood in front. Instead, as an intervention, they could be driving a higher vision truck that has a larger windshield, a lower driving position, and better sight lines. So in that situation, we were able to get, in this case, about 45 subjects. We were able to design an experiment in the simulated environment where no one's going to get hurt. It's very difficult to do this in the real world, but because we know simulated results are robustly correlated to real world results, we really can say that when we observed a crash rate of 87% in that top scenario where the little boy in the red sweater crosses and then maybe drops something or stops to tie his shoe, that's the outcome of the drivers either pulling forward on the green or stopping was extremely different. 87% of the time they would run over the person in that case, even though they could see, and our eye tracking software showed that indeed the drivers were looking and tracked that someone crossed from the left but did not exit out from the right. And this in our view was a major connection between the ability of a driver to see a pedestrian through line of sight and their likelihood of colliding and striking that pedestrian. Now, not every vehicle can be swapped out overnight, and the market for some of the high vision vehicles is still not where it would need to be able to do that. So what are some near-term mitigations? One that we're looking into is advanced types of camera systems. These are some that we've documented in the bus and truck space, but they're also available on light-duty vehicles, typically from the OEM. So we're in the process right now of using a VR simulation platform to examine how effectively they might help a driver prevent a collision with a person walking or biking in common scenarios. Becky, Ms. Bueller mentioned earlier, and we we are indebted to their team, and it's been a terrific partnership. We were able to actually just publish this paper that made early use of the blind zone measurement capability. So in addition to understanding how blind zone affects crash risk, we also wanted to ask the question, how have blind zones changed over time? And Sam showed us how the makeup of vehicles over time has changed. But even individual vehicles, if you look at a Honda CR-V from 1997 versus a Honda CR-V from 2022, they're not the same vehicle. And so this is the first time we believe that it's been possible to track how even vehicles have been increasing what you might call car bloat as the hoods have become taller, the pillars have in some cases become thicker, the belt lines also higher. And for the first time, we've been able to quantify using this tool. And you can take a look at this SAE paper that came out just a couple of weeks ago. And these types of maps are now make it possible to map out where a driver can and cannot see the pavement, where they can and cannot see a pedestrian, a child, an adult, and so forth. We've also done this in a low-tech way and mapped this out. And this is where the infrastructure starts to come in. Once we know and we can measure what adults and child pedestrians can't be seen by a driver, we start asking, well, where and when can they not be seen? And in this case, this is a study with Mass DOT where we use that same blind zone mapping approach. We mapped it against a crosswalk. This is that standard crosswalk you all saw the truck driver pull up to earlier in my presentation. Well, in a large number of these vehicles, the driver cannot see a child. Actually, about 2/3 of these makes and models, they can't see a child almost anywhere in the crosswalk. And in a smaller number, they can't even see an adult, right? About the bottom 4 trucks here, they can't see an adult anywhere at the crosswalk. The same exercise we've mapped against a bike lane. So you can see here, again, these are large trucks, but we also did this with medium and light duty vehicles, in all over 60 vehicles in the MassDOT study, which is publicly available. You can pull it up. Again, this is actually, in some cases, this is a more dire outcome because when we look at an elementary school representative child on a bicycle, and this is a buffered bike lane with a 2-foot offset, almost any vehicle prevents the driver from seeing that child in the bike lane, which you may imagine before a right turn is important to be able to see them without relying on mirrors, which have a longer response time, or sensors, which can have false positives and other pitfalls. So again, we can do these maps now. This is a high vision vehicle from our simulation mapped out using this method at the top. The drivers at the origin, and where they can see the pavement is the edge of that contour, the yellow contour. And here they can see out less than 5 meters ahead, more like 4 meters, about 12 feet. This low vision vehicle, they can't see until more than 35 feet out. They may not be able to see the pavement of an entire intersection. So speaking of intersections, what does that mean? And this is something that we're working on right now. This is next chapter in our work is bringing in the infrastructure. And we see a lot of opportunities here because while vehicles can be replaced and there's a fleet turnover cycle, there's also a turnover cycle for recapitalization, for repavement projects and small build projects in cities, counties, states. And there's a toolkit that we believe has the potential to help here and potential to help on a shorter timeline in some cases. So there's some geometric considerations like protected intersections or raised crosswalks. Just imagine a raised crosswalk that makes a pedestrian 6 inches taller. What's the effect on their risk of not being seen in the blind zone, or having a setback, pulled back stop bar that's perhaps enforced by near sight signal, and then introducing leading pedestrian intervals? What does that additional 3 to 7 second lead time allow in terms of the blind zone envelope? These are some things that we're actively looking into. just to highlight another area where we worked on, and this is another vehicle design issue that can be turned into an opportunity, is just side impact crashes involving large trucks. Speaking of blind zones, all of those bicyclists on the left cannot be seen by the driver in that truck when it's approaching the critical point of making that turn. And one countermeasure there is a design change as well to the vehicle, but it's not the front of the vehicle, it's the side of the large truck that has an exposed underside. These are lateral protection devices that can also serve as aerodynamic panels or aerodynamic side guards on the order of 4 to 7% fuel efficiency increase, depending on the drive cycle of the vehicle. And this is something that is an example where research has turned into real world implementation. You can see there, some high vision trucks at the top right that already have integrated side guards, and other vehicles that are older have retrofitted side guards as spread out as this map suggests. It's really across North America. This intervention that started in Europe, Japan, and throughout Asia and Australia has made it to North America. Really, it's been a grassroots kind of bottom-up intervention with some of the early policies going back over 10 years. Volpe's role there has been to help avoid a patchwork of different specifications by coming up with a model specification that has then been used for consistency. And I would say that has greatly helped in really over the last 10 years, a specific intervention taking off and making inroads across fleets in the country. There's another area of vehicle design, and this is almost taking a step back. Visibility, front end geometry, and the ability to fall under a vehicle and be crushed by the back wheels are all in some ways factors of the size of the vehicle. And if vehicles are larger than they need to be for a specific role, and this is thinking especially in a fleet environment, then right sizing or downsizing those vehicles presents an opportunity for improved safety. This is something that Seattle DOT, New York City DOT, just various municipal agencies are taking this as a new approach that can both save money. In some cases, it's operational. Maybe they don't need CDL drivers where they used to need CDL drivers by going to a smaller platform. But that vehicle at the top right used to be a large flatbed truck. Now it's a pickup truck with a smaller trailer. The vehicles at the bottom, the electric bikes, used to be a van or a box truck, and the sweeper at the top left used to be a much larger sweeper that could not be easily electrified. So this is something we've partnered with the likes of NACTO, National Association of City Transportation Officials, and quite a few cities over the years, providing case studies. There's an example of a snowplow that makes it possible to implement protected bike lanes, which then have their positive feedback loop of reducing crashes and injuries from crashes by reducing conflicts with motor vehicles. But when we've worked with fleets, it can be a bit of a question of where to start. Where do you start with these different interventions for safer vehicle design and technologies? And a helpful framework that others can use and that we're seeing being used more widely is this tiered approach. This is something we certainly did not invent, but we adapted with the New York City fleet, where tier 1 is something the fleet requires, tier 2 is something they deem a best practice and do wherever possible, tier 3 merits additional exploration. That operationalized becomes a table that then promulgates into contracts and procurement and guides the future safety investments of, in this case, a public agency, but it could be a private fleet or company. And this is something, like I said, has been more and more widely implemented, and just with the specific example of New York City at this point since 2017, when we started down that road, has resulted in over 100,000 discrete safety investments across their vehicle fleet, which is I think significant milestone. So like I said, what's next? We're going to be working on supporting more public and private fleets to lead by example. And when fleets lead, that can trickle down and help the economics for private vehicles, private vehicle owners as well. We're witnessing more state and local action in some of these areas, really recognizing that safe vehicles are part of a safe transportation system, and that it is a viable countermeasure at all levels of government and private sector organizations. And we're going to be really bringing in the infrastructure as well. So evaluating that blind zone safety reduction using infrastructure countermeasures as well as vehicle countermeasures once we know what those vehicle blind zones are. I'm happy to provide share a little preview of some of our thinking, and would love to get some thoughts from the audience. But putting some of these pieces together, this is a work in progress. But if anyone out there is also thinking about how to put together the blind zone envelope risk to, in this case, let's say be a bicyclist and be a pedestrian, how do we map out and develop performance metrics and then figure out how the risk of being struck at the intersection or any of a number of other scenarios, how can we mitigate that using the right countermeasures in the right place? Come talk to me. So I'll leave it at that, and back to you, Dan.
All right, thank you, Alex. We'll keep talking to you and bring everybody else back as well, because we've got some good questions to handle it. If you want to stop sharing your screen, I think we can get everybody's video up on the screen while we go through some of these. I think we've got time for most of them. I think we can, although if we don't get to your question, we apologize. Please do reach out to us directly. I don't know exactly where to start, so I might start with this big picture question, and then we can get into some specifics. But after hearing about all this promising technology and understanding the risks of certain designs and sizes that may increase the risk of injury, there are a lot of questions coming in about, well, who can get this into we can get this into vehicles, right? We know how to do it. It's just a matter of who's in the best position to push this forward. Should we be looking to manufacturers to take this on and build these into their vehicles? Is it the role of regulators where we need to be putting the attention? And what can local, regional, and state planners and engineers do? And Alex, you finished with a lot of that there about what can be done. But I wonder if maybe Sam and Becky, we started your presentations with you. We can go around the room and just think big picture about where the opportunities are for getting more of these technologies into vehicles and changing designs so that they're actually reflected in the fleet that we see on the road.
When it comes to like vehicle designs or even including specific technologies, I think, our standpoint has always been that regulation is the first place to go to set a minimum standard. So just like we do with crash testing, the regulations, the FMVSS are here to make sure nothing below a certain level. And so I think that would be the first most logical place to really drive change. But in situations like we may be in right now, where regulation, the government is not really pushing forward, it does potentially fall on folks like us to help provide consumers with information so that they can make safer, better vehicle decisions, and that will in turn get vehicle manufacturers to make those kinds of changes as well.
Greg, Alex, you have any thoughts on that?
I'll just follow on with Becky. I think she's spot on. The way that we have influenced regulation over the years, I think that's the collective we that we have on the call here, has been to point out the safety implications, to point out the deficiencies in current designs and test standards, and then to push the federal government to forward on regulation. In the absence of that, our partners at IIHS, Consumer Reports, and others have done a great job of creating an interim that encourages manufacturers to perform well with the technology, and then over time the federal government then picks it up. I think automatic emergency braking in general is the best example of that. We start with something, a relatively low bar, and make sure everybody can get over that bar, and then we give some time for the technology to develop. But we always have to remember, I know David Zuby used to remind us all the time that that it takes a minute, because the fleet is large, and any technology implemented today, even at 100%, would take more than a decade to get in half the cars on the road. So it's not a short-term deal.
Absolutely. Alex, any additional thoughts on that? I mean, one of the questions wrapped in there was the role that the local, regional, and state agencies can play in helping with this. And you spoke about, vehicle fleets and, public fleets, and, you can make decisions about what those vehicles can do. Anything else you have to recommend?
Yeah, Dan, I think any level of government has more leverage than they probably realize, because almost any agency operates a fleet or contracts with actors who do. And they have a supply chain, they have procurement authorities, and they can lead by example, and they're increasingly doing that. Typically, in my observation, starting within the scope of their own organization, and then looking for ways to go to their supply chain and their contractor base. And just like they would for other policy factors, they would consider that. They consider that part of their footprint of their safety. So that's one area. The other thing I'm thinking about, in terms of procurement, is just sending a unified demand signal. I'm thinking it was about 8 years ago that hundreds of cities got together and put together an RFI for electric vehicles at the time. And that was a demand signal that, hey, if vehicles with this performance envelope, in this case would be safety, right, were made available, we would want to buy them. And that's something that can be done. That's something that was done by that organization of mayors, and something I think could be done here. There's also state and local. We're witnessing in real time the multiple states recognizing, and at least in some use cases, the importance of intelligent speed assistance as a tool. Over in Virginia and Georgia and Washington, elsewhere. So I think the message is one of empowerment, and everyone has complementary roles and authorities to make a difference.
That's great. Thank you for that. We had a few questions. I don't know that we touched on this issue exactly, but some general questions about, these factors as they relate to crashes involving people with disabilities, especially blind pedestrians and people with low vision. I'm particularly curious about that as a risk factor in the issues you all looked at in your work, and then specifically on the automatic emergency braking and pedestrian detection, pedestrians in wheelchairs and that different shape. I apologize if I missed that part of your presentation, Greg, but if you could speak to that as well. How are we acknowledging maybe the additional risk of a person with a disability in a crash involving a vehicle when we think about these technologies and these designs? I didn't call on anybody first, but yeah, Greg, please.
Sure. I'll take the last part first. It's a challenge. Automakers and suppliers that are designing these automatic emergency braking systems are trying to do so within the confines of what's reasonable in terms of cost and complexity for the systems. And as a result, they're designing, unfortunately, around the middle of the curve. And some of those edge cases are not well populated in terms of the performance set of the systems. persons with disabilities. While we have not tested that directly, my guess is that it would not fare very well. We've done some testing with bicyclists because there are some bicyclist platforms that we can use. I've tried to use interns for these things and they don't let me for some reason. I don't quite understand, but so we have to wait until there's a platform developed in order to be able to test it. And I suspect that as a result of the absence of said platforms, the automakers are not designing around that quite yet. It gets quite expensive to hit things that create damage to the car. So unfortunately, not great news for those folks that may be in a wheelchair.
Thank you for that. And on anything related to blind and low vision pedestrians, a few people in the questions have brought up the issue of quieter vehicles as a and that may be outside the scope of some of the research we've heard about today. But if you have thoughts on those issues, I'd love to hear them. Becky and Sam, oh, you're on mute. I'm sorry, Becky.
We have done some studies looking at hybrids, I think specifically, and pedestrians, and have found that quieter vehicles are, a bigger risk because pedestrians may not react or hear that a vehicle's coming. But there are some, again, a place where regulation can play a role. There are now some regulations that the vehicle must make some sort of noise to alert the pedestrian. And so, that's something that we could probably study again in the future to see if that situation has improved. And if it hasn't, make recommendations as to how to strengthen that or improve the audible ability to recognize the vehicles coming.
Yeah, about 10 years ago, Volpe, actually, when I first started Volpe, it was one of my first projects, was working on some of the research for the minimum sound requirement at the time. Interestingly, though, that only applies to vehicles up to 10,000 pounds. So as we do see more electrification in just quieter vehicles in over 10,000 pounds. So think about larger pickup trucks or work trucks, buses. Those aren't necessarily those are not subject to that. So, which was maybe not very foreseeable 10, 15 years ago. But
thank you for that. I had a question about for Greg. This one's for you. Automatic emergency braking technology, ADAS. What technology specifically are used in that system to detect pedestrians? This person's asking radar, LiDAR, ultrasonic video. Can you tell us a little more about how that technology works? How are people seen, I guess?
Yeah, unfortunately, it is primarily reliant on camera based technologies, and then with some augmentation from radar. Radar doesn't do a great job of object detection. You have to rely on the cameras for that, and so the engineers that are working on that sensor fusion sort of bias it to the camera input. It's part of the reason they didn't perform very well at night, because without the contrast that is provided by the lighting to the camera, it just looks like a blank canvas. There are solutions out there, particularly infrared, that could help this pedestrian situation at night. And we are hopeful that some form of the new FMVSS standard on this goes forward and will, through that, encourage automakers to begin integration of infrared technology. If it's warm and it's moving in front of the car, we should probably stop for it. And that sort of takes the complexity out of the equation, and hopefully we see more of that. It's just a matter of the standard didn't require it, so automakers aren't installing it. So we don't see the effectiveness there yet. So we're hopeful that that new standard pushes that forward.
Becky and Sam, we had a question about your study specifically. That we're in the cases where the HLE, the leading edge, was less than PED. So I think that's where it's much shorter than the pedestrian height, if I recall correctly. Was there a way to tease out within those incidents where the pedestrian sustained an injury, a head injury by striking the windshield versus the hood of the car? Could you get to that level of granularity? Do we know more about where the strike happens and that sort of thing?
We would be able to. The study that we conducted focused primarily on the torso, the thorax area. But we're hoping to write up a more extensive study that looks at all the body regions, so we definitely can identify those differences there, and with the hopes of providing information to NHTSA or others who are running impactor tests to say, hey, these really tall vehicles, here's where your test zone should be, versus these really short vehicles, here's where the test zone is, to have maximum, relevance to real world scenarios.
Yeah, everything that Becky just said, I agree with, definitely. Something that we did find, not in terms of the relative height measures, but just in general, is that head injuries were most common from impacts with the hood. So they did happen in other areas as well, but the hood impact, especially for those taller, blunter vehicles, was what tended to cause that. And you can kind of understand why that's the case when Becky showed her wireframe image of basically the whole front end hits your torso, and then your head kind of goes over and hits the hood.
Yeah, very interesting. We can and everyone, we can look back at some of that content when we post the recording, and the slides are available too if you want to compare visuals on what we're talking about here. Alex, the next one for you, but I'd love to get the entire panel to weigh in on this as well. And I think we've been talking about a lot of technologies that are likely going to be only available in new vehicles being sold, but there were questions about the potential for retrofits of existing vehicles and whether any of these technologies that we're talking about, and maybe others that we haven't even mentioned, could be, have the potential for being retrofit onto older vehicles. And my mind goes to truck side guards, because I think, I don't know, you've done a lot of work on that, but I think that can be a retrofit onto a large vehicle. But what we're talking about here today, ADAS and AEB, certainly hood shape, I don't know if I see a lot of potential for retrofits, but maybe I'm wrong.
It's a good question because of what Greg was saying. Even 100% penetration of OEM tech in 10 years, you're only halfway there. So what can we do today? And intelligent speed assist it really jumps out to me as one where the aftermarket or retrofit is a major solution, because that can be plugged into the OBD port, and it's a 1-hour install. So in fact, we're planning on piloting it at our own agency in about a month. So we'll see how that goes. But and that's that helps address a class of crashes related to speeding. But there are other aftermarket or retrofittable solutions as well. And just thinking about it, there are forward collision warnings that can be installed. You can't generally install automatic braking as a retrofit, unfortunately, with some exceptions. For air brake vehicles, you can install there is a rear automatic emergency brake that you can retrofit on air brake vehicles. So it's used somewhat in the construction industry and sanitation industry. There are more typically, it'll be driver alert. So for example, a 360-degree camera that stitches together the forward, side, and rear views for near field visibility. So if you have a large blind zone in the vehicle, or if you're in a truck, even the high vision truck, you're not going to see behind the cab very well. That can, that is certainly aftermarket, and more of those are getting some amount of AI-based enhancement, where they might be classifying and identifying, is this a person or is this a trash can, and perhaps highlighting that for the driver. That we're in early days of understanding the effectiveness of some of those, but certainly mirrors, traditional camera replacements for the side mirrors, backup cameras obviously can be retrofitted. And if your vehicle is more than 10,000 pounds, it's not required to have a camera, at least federally, for backing up. But that's something you can easily retrofit. So I think, yes, and the Safe Fleet Transition Plan from New York City can be a helpful template to see what some of those OEM versus aftermarket technologies are.
Becky, Sam, Greg, any other ideas, thoughts on retrofits? What technologies might be right for older vehicles to be equipped with?
As Alex mentioned, there are several systems out there aftermarket available, and we've tested a couple of them. They work reasonably well-ish. It's certainly, it's like my wife says about me, it's better than nothing. And so I think the important thing is that it, you're not going to mandate that. So those would only be willing and interested consumers that, that would be interested in an aftermarket system. I think, as Alex points out, some of the commercial applications of that are probably the best place for that, because the fleet can mandate it. The people that are, individually interested in that kind of technology are probably pretty careful drivers anyhow. And we may not see a big increase in the effectiveness from the aftermarket side. And it's challenging because vehicles are so diverse in the way that they operate.
Anything to add, Becky or Sam? Retrofit issue? Oh, you're muted, Becky. I'm sorry.
I think the issue of pedestrians really is a safe systems approach issue, and we need to not just consider the vehicle design, but also the environment, speeds, the people. And so I think the near-term fixes, because vehicle design will take a while, even if we, have 100% compliance tomorrow, is to try to work with communities, Sam's study looking at those different speeds and the different heights and the injury risks. If we can get communities to have speed limits that are in those zones where the height of the vehicle doesn't make a difference, lowering those speed limits, making pedestrians more obvious, having the blinking crosswalks, getting people to be more active at scanning and looking for pedestrians where pedestrians are likely to be. Those are things that we can do in the near term.
Yeah, so I mean, we found that, so under the safe systems approach, a safe crash speed is one where there's a 10% or less chance of a serious injury being inflicted. We found that crash speed using US vehicles to be 15 miles an hour approximately. Obviously that's not always going to be feasible. You could think about that maybe in terms of like city centers or super densely populated areas. But I think an important thing to take away from speed reduction is that even very small reductions in speed can have a huge impact on crash risk. So, for example, we found that if you go from a 30-mile-an-hour crash to a 25-mile-an-hour crash, the risk of serious injury is literally cut in half. So, even reducing it by a small amount can make a big difference. If you can't, make it to 15, then maybe consider cutting it ever so slightly.
Well, and you've queued me up perfectly for the final question I wanted to get to is, and we had a lot of questions about this, is what environmental changes can we be making that will enable these technologies to work better, or as you're saying, that will help us achieve our goals while we await more saturation in the fleets. And maybe I'll ask, are there specific promising changes to roadway design operations that you might recommend people looking into? We're hearing a lot about, you're sharing a lot about speed reduction through roadway design, for example. Are there other strategies within that realm that you might point people to? Alex, I might start with you if that's all right.
Sure,
Yeah.
sure, yes. I know we have just a few minutes, but I think that is a really promising area. As Becky was saying, increasing lighting in the right places to improve pedestrian visibility. We don't necessarily have a grasp on how well our crosswalks are lit. Are they lit correctly or not? We have a pilot research project with some students right now. Stay tuned in a month. We'll hopefully have some results. But there are just some well-known interventions already, like leading pedestrian interval or restricting turns on red. That's when a driver is looking left while they're turning right and striking a pedestrian in the crosswalk. These are very low cost, quick interventions in some cases. Others are a little more capital intensive, like raising crosswalks. But now you think about it, well, if our blind zone analysis says you can see a child, X% more of the time in a school zone, maybe that's an extra reason for that as a proven safety countermeasure. Federal Highway has proven safety countermeasures, but they haven't necessarily been looked at through that lens before. And I think there may be just a real toolkit that we're sitting on in some of these cases to reduce speed, increase the time that a driver has to see another person on the road and react. And we can be making our planning, we can be planning those interventions with a more informed perspective once we measure what we treasure. Then we manage what we measure.
Thank you. Greg, any thoughts on, roadway design changes that can help enable these systems to work better? Yeah.
Yeah, just real quick, like I mentioned, overhead lighting is critical. There's two reasons for that. One, as I mentioned, the current systems rely too heavily on cameras to accomplish it, so light is necessary for them to be effective. And two is that the headlight standards in the US and our headlights are generally pretty inadequate. Getting better, but also creating glare, which is a whole other, challenge for scenario, for pedestrians as well. So it's another reason to ensure that we have overhead lighting to minimize the need for headlights that are so glaring as well. So yeah, I think that's the short version for me.
Becky, Sam, anything else to add? I know you started off with some of those ideas. Yeah.
Yeah, I mean, we have folks that are transportation engineers that are studying various countermeasures and looking at all of these aspects. I don't think it's either Sam or my specialty, so they're not here today, but there's definitely work that we're doing to try to cover all those bases to see how we can best improve each one of those pieces to really improve for both pedestrians and other vulnerable road users.
I would just say yes, and as far as infrastructure and vehicle countermeasures.
Unmute there. Thank you very much for all those responses. We are out of time for Q&A, unfortunately, but it was a lively discussion, great presentations. I think you've all now, with our slides, you have our contact information. Encourage you to reach out to us with any other questions that you have. We didn't get to yours. I'll remind you now that we will have an email coming to you with information about completing the post-webinar questionnaire, getting your certificate of attendance. We'll remind you where the recording and the slides can be found. And so, again, we really appreciate your time today and hope to see you on the next one. So thank you all again.